Greetings to everyone. I am Dr. R. Rajaram, Assistant Professor at the Department of Chemistry in Madanapalli Institute of Technology and Science, Andhra Pradesh. Today we are going to discuss about conductive metric titrations. Actually, there are volumetric titrations. There are some few differences between volumetric and conductive metric titrations. In volumetric titrations, we'll have a burette. In the burette, titrate will be filled. The conical flask will take the titrate along with the indicator. Here titrant will be there, here titrate plus indicator. Actually, titrant is the one whose a solution whose concentration is known, that is called titrant. Usually that we will take it in burette. Titrate whose concentration is unknown, that's what we are going to measure, that is called titrate. That will be taken in the conical flask along with the indicator. In case of some titrations like KMNO4 versus oxalic acid, we are not going to use any indicator, because in this case KMNO4 itself will act as a self indicator. If you take HCl versus NaOH, there we will determine concentration of HCl with the help of NaOH or vice versa, where if your sodium hydroxide is taken as the uh, titrant, HCl will be taken in the conical flask along with the indicator called phenolphthalein. Anyway, in volumetric titrations, either we have to use the external indicator or we have to use the self indicator. But in some titration, in case of conductometric titrations, we are not going to use any indicators. Instead of indicators, we are going to measure. In the absence of indicator, we are going to measure with the help of sorry. In the absence of indicator, we are going to measure the concentration of the unknown sample with the help of conductometric titrations. Here, say for example, if we take HCl versus NaOH, here we have to determine the strength of HCl using sodium hydroxide in the absence of indicator. Here, HCl is inferred as a acid, means strong acid. Sodium hydroxide is the strong base. According to Arrhenius theory, any substance can be defined as acid if it releases H plus ions in the solutions. In case of base, if the any substance that releases OH minus ions in the solutions, they are referred as base. What do you mean by strong acid or strong base? Means any acid that will dissociate completely to give the anions as well as cation is called H plus, and the cation is called strong acid. Any base that dissociate completely to give OH minus ions are called strong bases. So some acids like acetic acid, they will not dissociate completely to give the respective acetate as well as H plus ions. Those kind of acids are inferred as weak acids. So here we are going to determine the strength of the strong acid with the help of the strong base. In this case, usually this titrate, that is sodium hydroxide, will be taken in the burette. Here, HCl will be taken in the beaker. Here, if we are drawing a graph like this, volume of sodium hydroxide in ml, here conductance. So at first, we are taking the conductance of pure HCl. since it is completely dissociated, all the H plus ions are free to move in the electrolyte. They are free to move. Since it is completely free to move, and at the initial stage of the reaction, the conductance of the solution is very high. Right? Now, if we add 1 ml of sodium hydroxide, if we add 1 ml of sodium hydroxide, the conductance will fall. That is due to the neutralization of HCl ions. Right? Now, why it is why it is decreasing? It is due to the neutralization of HCl ions. Now, if we add second ml of sodium hydroxide, the conductance will still fall. The conductance will still fall. Means excess of whatever the HCl ion is present in the solution, it is still neutralized. Likewise, if we add excess of sodium hydroxide, the conductance will fall in a linear fashion. Third ml, fourth ml, fifth ml, sixth ml, seventh ml. After this point, after the neutralization point, the conductance will start to increase, because if you take the reactions HCl plus, since HCl exists as H plus and Cl minus ions, I will write it like this: H plus and Cl minus ions plus Na plus and OH minus ions, because that is also weak base. Sorry, that is also strong base. This is also strong acid. They will exist as ions in the solutions. Once they are reacting, this acid and this base will lead to the formation of the salt. Here also I'll write it like this, because the salt will be in Na plus and Cl minus. Finally H2O, that will not exist as ions. So when the solution contains excess of H plus ions, when it is treated with OH minus ions, that is neutralized. We keep on neutralizing, the, that will reach the neutralization point. After one point, after the neutralization point, the ions will, the conductance will start to increase from this point after the neutralization point, because here the conductance is due to the mobility of H plus ions. Here the conductance is due to the excess of OH minus ions. After the neutralization point, if we add sodium hydroxide into this solution, there will be the excess of OH minus ions. That ions will move in the electrolyte. Since it moves in the electrolyte, uh, as fast as your as the mobility of the ions is similar to the H plus ions. Since the mobility is similar, we can obtain the increment in the conductivity. Similar, even even at this neutralization point, the conductance is not zero. That is not zero, because in the solution we'll have sodium chloride ions. These sodium and chloride ions will move in the electrolyte, but since the mobility is very slow, the conductance value, the current value we are obtaining is slow. We could not expect that at the neutralization point. At the neutralization point, we could not expect zero conductance, because due to the existence of Na plus and Cl minus ions. So, even in the absence of indicators, we are able to determine the strength of the given acid using conductometric titrations. This is where are we using this? So the applications. So before the applications, let us discuss about the um, advantages. Where are all we using the conductometric titration? First one is advantage. First one is we can run the titration in the absence of indicators. Right? It is suitable for dilute solutions. It is suitable for dilute solution, turbid solutions. In addition to that, it is suitable for incomplete reactions. Incomplete reactions. Similarly, the advantages of this conductibility, there are so many. We are pointing out few, but it is associated with some disadvantages also. So, what are the disadvantages? Here, if the excess of electrolyte, if any other foreign electrolyte other than the electrolyte of interest is present, means we could not identify the endpoint accurately. So, in the presence of excess, sorry, uh, other electrolytes. The second one, when the high concentration of salt is present in the solution. When the high concentration of salt is present, there also we could not expect the accurate value. In case of this redox titrations, in case of redox titrations also, we could not expect this value. We could not expect the accurate value. The advantage, the applications of this conductometric titrations are, I'll say, the applications mostly, the applications of this conductometric titration mostly it is used for environmental monitoring. It is used to determine the purity of water samples. Right? No, it is used to determine the alkalinity of water. It is used to determine the salinity of water. Likewise, there are so many applications with these titrations. So the ultimate, in order to sum up this conductometric titrations, there are number of conductometric titrations. There we can deal with strong acid versus strong base. There we can deal with strong acid versus strong base. Weak acid versus strong base. A combination of strong and weak acid versus strong base. Strong acid versus weak base. Finally, precipitation reactions. So in the subsequent meetings, we will discuss them one by one. Today we have discussed with strong acid versus strong base. So acid is a one. When it is placed in a solvent, it releases H plus ion. If it releases H plus ions, that is inferred as acid according to Arrhenius theory. Any substance, if it releases OH minus ions, and when it is placed in the solvent, they are inferred as strong bases. If the dissociation is complete, it means they are completely dissociated into H plus and the respective cations, or OH minus and the respective anions. Sorry. If the acid is completely dissociated to H plus and the respective anion, and OH minus ion and the respective cations completely. If the dissociation is complete, those kind of acids as well as bases are inferred as strong acid as well as strong base. If the dissociation is incomplete or poorly dissociated, those kind of acids as well as bases are inferred as weak acids or week basis. So with this, we will come to the end of the lecture. In the subsequent lectures, we will see the rest of the rest of the conductometric titrations. That's all.